Assalamu alaikum. My name is Umme Habiba. I'm from Chemistry Department. Today, topic of my presentation is Introduction of Carbohydrates and Monosaccharides, which is one of the main topics of organic chemistry. First of all, we see contents, which include introduction of carbohydrate, monosaccharides, which is one of the main classes of carbohydrates, introduction of monosaccharides, their structures, properties, then classification. After that, I'll discuss reactions of monosaccharides, ester and ether formation, oxidation reaction, reduction reaction, glycoside formation, mole degradation, then moving towards essential monosaccharides. First of all, we see what are carbohydrates. The word carbohydrate derives historically from the fact that glucose, the first simple carbohydrate to be obtained in pure form, has the molecular formula C6H12O6 and was originally thought to be a hydrate of carbon. Today, the term carbohydrate is used to refer loosely to the broad class of polyhydroxylated aldehydes and ketones, commonly called sugars. Glucose is most familiar example, like this is open chain form of the structure of glucose and it is ring structure. Then classification of carbohydrates. Carbohydrates are basically classified into two main classes, simple and complex. Simple carbohydrates are further classified into two classes, monosaccharides and disaccharides, but complex carbohydrates are polysaccharides. Glucose and lactose are examples of the simple carbohydrates, and starches and fibers are examples of the complex carbohydrates. So here we see introduction of monosaccharides. A monosaccharide, a simple sugar, is a carbohydrate that can't be hydrolyzed into smaller carbohydrates. So like all carbohydrates, a monosaccharide also consists of three main chemical elements: carbon, hydrogen, and oxygen. It is the simplest type of a carbohydrate molecule and often serves as the basis for forming more complex molecules like polysaccharides and disaccharides. Then properties of the monosaccharides. In pure form, monosaccharides are crystalline, water-soluble, colorless solids. Monosaccharides have a sweet flavor because the orientation of the hydroxyl group interacts with the taste receptor on the tongue, and when they interact with our taste receptors, we feel sweetness. So through a dehydration reaction, two monosaccharides can form a disaccharide, 3 to 10 can form an oligosaccharide, and more than 10 can form a polysaccharide. Then structures of monosaccharide. Monosaccharides may exist as straight chain molecules or as ring structures. For example, in the figure you can see it is the acyclic or open chain structure of fibers and it is cyclic structure of ribose. The ketone or aldehyde group of a straight chain molecule can reversibly react with the hydroxyl group on another carbon to form a heterocyclic ring. In the ring, an oxygen atom bridges two carbon atoms. So they form two main shapes. If rings made of five atoms, they are called furanose sugars, while those consisting of six atoms, they are called pyranose formed sugar. And in nature, the straight chain furanose and pyranose forms exist in equilibrium. Calling a molecule glucose could refer to a straight chain glucose, glucofuranose, glucopyranose, or a mixture of the form. Then we see classification of monosaccharides. Monosaccharides are further classified as either aldoses or ketoses. The O suffix designates a carbohydrate, and the alto and keto prefixes identify the kind of carbonyl group in the molecule, whether aldehyde or ketone. The number of carbon atoms in the monosaccharide is indicated by the appropriate numerical prefix like tri, tetra, pentax, and so forth in the name. Glucose is an aldohexose, It's mean a 6 carbon aldehyde sugar. Fructose is a ketohexose. It's mean a 6 carbon keto sugar. Ribose is an aldopentose. It's mean a 5 carbon aldehyde sugar. And Acetoheptulose is a ketoheptose, a 7 carbon keto sugar. Most of the common simple sugars are either pentoses or hexoses, as we discussed above. And aldoses have more than one hydroxyl group and a carbonyl group at the terminal carbon, while ketoses have the hydroxyl group and carbonyl group attached to the second carbon atom. And it is the main difference of their chemistry. Then we see reactions. First important reaction of monosaccharide is ester and ether formation. Monosaccharides behave as simple alcohols in much of their chemistry. For example, hydroxyl groups in carbohydrate can be converted into esters and ethers, which are often easier to work with than the free sugars. Because of their many hydroxyl groups, monosaccharides are usually soluble in water but insoluble in organic solvents such as ether, and they are also difficult to purify and tend to form zeros rather than crystals when water is removed. Ester and ether derivatives are soluble in organic solvents and are easily purified and crystallized. Then esterification is normally carried out by treating a carbohydrate with an acid chloride or acid anhydride in the presence of the base. For example, in this reaction you can see beta-D-glucopyranose is converted into penta-O-acetyl beta-D-glucopyranose in the presence of acetic anhydride, and the reaction is carried out in the presence of protein under the 0 degrees Celsius temperature. Then carbohydrates are converted into ethers by treating with an alkyl halide in the presence of base. Standard Williamson condition using a strong base tend to degrade sensitive sugar molecules, but silver oxide works well as mild base and gives high yields of others. For example, in this reaction, alpha D glucopyranose is converted into its pentamethyl ether with a percentage of 85, and it is converted into its pentamethyl ether in 85% yield on reaction with iodomethane or methyl iodide and silver oxide. Then we see second important reaction, which is glycoside formation, and acetyl derivatives formed when a monosaccharide reacts with an alcohol in the presence of an acid catalyst are called glycosides. Actually, this reaction is illustrated for glucose and methanol. Then we see naming. In naming of glycosides, the O suffix of the sugar name is replaced by oside, and the alcohol group name is placed first. And as it is generally true for most acetals, glycoside formation involves the loss of an equivalent of water. The diether product is stable to base and alkaline oxidants such as Tollens reagent. Since acid catalyzed aldolization is reversible, glycosides may be hydrolyzed back to their alcohol and sugar components by aqueous acid. The anomeric methyl glycosides are formed in an equilibrium ratio of 66% alpha to 34% beta. Piano rings prefer chair conformations in which the largest number of substituents are equatorial. In the case of glucose, the substituents on the beta anomer are all equatorial, whereas the substituent on carbon number 1 in the alpha anomer changes to axial. Since substituents on cyclohexane rings prefer an equatorial location over axial, because methoxycyclohexane is 75% equatorial. The preference for alpha glucopyranoside formation is unexpected and referred to as the anomeric effect. Like in this reaction, both anomeric glycosides are stable to base and are not oxidized by Tollens reagent. Then there are some monosaccharides which are natural, like salicin, one of the oldest herbal remedies now was the model for the synthetic analgesic aspirin, a large class of hydroxylated aromatic oxonium cations called anthocyanins, provide the red, purple, and blue colors of many flowers, fruits, and some vegetables. Peonin is one of the examples of this class of natural pigments which exhibit a pronounced pH color dependence. The oxonium moiety is only stable in acidic environments and the color changes or disappears when base is added. Then the third important reaction of Monosaccharide is the whole degradation. The whole degradation shortens an aldose chain by one carbon. Whole degradation is the almost the exact position of Fischer sequence. That is, the aldehyde carbonyl group is first converted into a nitrile, and the resulting cyanohydrin loses hydrogen cyanide under basic conditions, the reverse of a nucleophilic addition reaction. Conversion of an aldehyde into nitrile is accomplished by the treatment of endose with hydroxyl amine to give an amine, followed by the dehydration of the oxime with acetic anhydride. The whole degradation doesn't give the particularly high yields of chain shortener doses, but the reaction is general for all aldopentose and aldohexose sugars. For example, in this reaction, you can see D-galactose is converted by whole degradation in D-lactose. D-galactose reacts with hydroxyl amine to form D-galactose oxide, and it reacts with acetic anhydride to form cyanohydride, and it forms with um, sodium methoxyoxide to form D-lactose. And the percentage is 37, and another product is also formed, which is hydrogen cyanide. Actually, it is removed. Then oxidation reaction. Oxidation of monosaccharides like other aldehydes, aldoses are easily oxidized to yield the corresponding carboxylic acid called aldonic acids. In this reaction, D-glucose form aldonic acid in presence of bromine water and pH is 6. The oxidation of aldose with either aqueous ammonia with aqueous sodium nitrate form the basis of simple tests for what are called deducing sugars. Actually, they are different reagents, either this silver or copper with sodium aqueous citrate. So Tollens reagent and Benedict's reagent. The oxidation takes place either one of the reagents and form the basis of simple tests for what are called reducing sugars. Reducing because the aldose reduces the metal oxidizing agent. Some simple diabetes self-test kits sold in drugstores still use Benedict's reagent to detect glucose in urine, though more modern methods have largely replaced it. It is one of the applications. And then all aldoses are reducing sugars because they contain an aldehyde group, but some ketoses are reducing sugars as well. Fructose reduces tolerance region, for example, even though it contains no aldehyde group. But reduction occurs because fructose is readily isomerized to a mixture of aldoses, glucose and mannose. In basic solution by series of ketoenol tautomeride sheets. Glycosides, however, are non-reducing because the acetyl group is not hydrolyzed to an aldehyde under basic conditions. So D-fructose when react with sodium hydroxide and in the presence of water form indiol and in the presence of sodium hydroxide water form D-glucose and D-mannose 2 units. And if warm dilute nitric acid is used as oxidizing and aldose is oxidized to a dicarboxylic acid called an aldaric acid, like in this reaction, this process takes place. D-glucose reacts in the presence of heat with nitric acid and water and form an aldaric acid. Finally, if the CH2OH hydroxyl methyl end of an aldose is oxidized without affecting the aldehyde group, the product is monocarboxylic acid called a uranic acid. The reaction can only be done enzymatically. No chemical reagent is known that can accomplish this selective oxidation in the laboratory. So it takes place just enzymatically, like D-glucose under a specific enzyme form uranic acid. Then reduction. Treatment of endose are ketos with sodium borohydride reduces it to a polyalcohol called an alditol. The reduction occurs by the reaction of open chain form present in the aldehyde ketone hemiacetal equilibrium. Although only a small amount of the open chain form is present at any given time, the small amount is reduced. More is produced by opening of the pianose form. Then additional amount is reduced and so on until the entire sample has undergone reaction, like beta D glucopionose form d sorbitol in presence of sodium borohydride and in the presence of water. Then we see 8 essential monosaccharides. Human need to obtain 8 monosaccharides for proper functioning. So we see, although it can be biosynthesized from simpler precursor, if necessary, it's more energetically efficient to obtain them from the diet. They are alpha-glucose, D-galactose, D-glucose, D-mannose, and so on. One of the 8 essential monosaccharide, galactose, glucose, and mannose are simple aldohexoses, while xylose is an aldopentose. Because it's a deoxy sugar, meaning that it has the oxygen atom missing. So there are structures of 8 essential monosaccharides: alpha-glucose, D-galactose, D-glucose, D-mannose, and acetyl D glucosamine, and acetyl D galactosamine, and acetyl D uh, neura, um, neuraminic acid, and D-xylose. Then, at last, we see what are function of monosaccharides. Monosaccharides serve two main functions within a cell. They're used to store and produce energy. Glucose is a particularly important energy molecule. Energy is released when its chemical bonds are broken. Monosaccharides are also used as building blocks to form more complex sugars, which are important structural elements. So it was a brief presentation on introduction of carbohydrates and one of the main classes of carbohydrates. So thank you.